Okay, so let's talk with the third part of the talk.
All right, so now we are going to go to a slightly more fun stuff, right? More recent as well. All right, so I'm back here and I want to say something on this joint law, right? And when I'm thinking of this, right, the natural idea is to say that I would like to compare the joint law with f bar tensorized m times. Now that becomes extremely tricky because I have the curse of dimensionality. There are not so many quantities that I can use to do this. Fortunately for me, there's one that has been identified a long time ago, and it's the use of the Gibbs entropy. So I am going to look at that object. And the 1 over n here is absolutely critical to get something of order 1. And this you can see because if Fn is tensorized as well, right, then this now would become just the standard relative entropy between the two tensorized things. If Fn was F tensorized n time, Hn is just the interval of F above F over F bar. That has the right scale. And it turns out that this quantity is also subadditive, right? And we've heard a lot about how subadditivity is important. And it's critical here as well because, and the reason it's subadditive now is just that x log x is a convex function. And here, the subadditivity implies the following thing. You get a control on the relative entropy of any marginal by Hn. This is trivial to prove for k equal 1 because you just symmetrize the whole thing and then you just use the convexity of x log x, right? So a little bit more work for k different than 1 because of how you're going to tensorize the corresponding objects here, but that's still completely doable. And so this is the quantity that we want to use. Again, as I said, there are not so many things that we could do if we want to compare stuff with the full joint law. And in particular, I want to emphasize the following thing. If you want to use an LP norm, for example, L1, it typically doesn't work. And the reason it doesn't work is if I compare in L1, right, tensorized version, and this in general is going to be something like this, and you lose a factor n. So what this tells you is if initially I have two IID processes, right? And they are close to each other. And in the total variation of their joint law, they are not going to be close to each other. There is no reason. I would expect this to be of order 1. L1 is bad, for example. All right. So before we start doing estimates on Hn, right? So the estimate is going to be, I'm going to take d over dt and do calculations. And then some terms will show up. And before we go there, I need a good large deviation type of inequality. And here is the theorem. So the integral f bar n exponential integral xy over c. This is less or equal than 2, for example. And there is an m here. Okay, so this is a large deviation type of scale, right? I'm comparing mu n. Now mu n, remember, is in that case, if you know the xi, then you know mu n, which is a measure on the corresponding underlying space, right? So in here, mu n is a random measure. And I know it's slow. It's slow. It's given by this, right? Because this controls the law of each of the xi. All right, so I have a random measure given by IID processes. I compare it with a limit, f bar. I compare it in an exponential scale against test functions. The logic, right, is that this should be like 1 over square root of n. So if I square, this should be like 1 over n. And I multiply by an n factor, so this should be of order 1. And that's exactly what the theorem says. Now, if phi is continuous, this is something you can get through standard large deviation arguments because that will give you the limit. But you need to take a limit, right? So, and here everything is explicit in terms of n. And in particular, the constant c only depends on the L infinite norm of phi. Well, nothing here is actually trivial. The standard large deviation estimates require work as well, right? So I'm really going to need it with 2 variables. So I'm writing it with 2 variables, and you will see that this is really the right form. This will, once I've got the nice bound on the relative entropy, this will also directly control the fluctuations. So this is something that will actually allow me to derive an equation on the fluctuations, well, likely tomorrow at this point. But so this is going to be a very, very important tool for us. And it's a relatively recent result. It's something that we proved with my student a few years ago. A very horrible proof. Okay. Very pedestrian. We basically express this in terms of the whole series, and then did combinatorics to track correctly the cancellations. And a few years after, there was a much better proof by people from Duke. Jonathan knows well, right? So Lim, Liu, and Nolan actually showed how you can prove that in a much simpler manner. So I'm going to briefly explain this. All right, so this is something that the first point is that to get exponential bounds, you actually only need LP bounds, but you need to understand how the LP bounds are behaving. I have a random variable, right? And its LP bound is like P. Then there exists a constant such that the exponential is bounded. This is a very simple argument that I'm just going to admit. Okay. You see that here, if I had one, right, so something that you may know is if the LP bounds are independent of P, then you actually have an L infinity bound.
This is just some power set.
Yeah. That's one way of doing it. Another way is to use level sets. Just tons of very simple proof of that fact, right? And basically, whenever you have something here that is growing, depending on how fast it grows, it gives you a certain function here that you can derive. Right? So it turns out the growth for exponential is linear in the exponent. All right, so we want to control something like this. And then what those guys observed is that there is a still relatively recent result that generalizes the sort of notion of square function, Littlewood palette theory to martingales, and that we can use to get away with bounding that in a very simple manner. Following result by Rio. Take Fk of filtration, right? So as usual, something that is growing. Mk that are martingale differences. So Mk have to be in LP and right, and Mk is Fk measurable, of course. Then you have a square function argument. So I want to control LP. And I'm going to put a square, and I'll try not to mess up the constant too much. So I'm using a P. And then I have a summary I of MKP. That's a very neat generalization, again, of the square function for functions, right? If you just project on annulus in Fourier, this is exactly the same sort of representation that you have of sublative spaces in general, right? And here for us, that's wonderful. Because we naturally have an expression of those objects in terms of applying twice this theorem.
The next equation is on the right hand side, right? Or else it's
Yes.
on the left hand side.
Yes.
That's what you got to show.
Yes.
K equals I.
Okay, so you're summing over K. That's what you're saying.
And I'm summing over K, not I. Thank you. All right, now it should be good. And this is what? This is the expectation, right? With respect to this F bar n of a double sum. because mu n will just give me those objects, right? And then whenever I integrate with respect to f bar, right, the only thing I have here is I get away with an expectation. So this is something I can represent as the double sum of the, so 1 over n, the sum over ij, the sum phi tilde xi bar xj bar LP. Right, that's what we need. With the fact that in phi bar, I've taken a conditional expectation in each variable so that they vanish automatically, right? So the expectation of phi tilde of xi bar xj bar given xi bar is 0, for example, right? And the symmetric. And that's just because of the minus f bar here. I'm just going to decompose my double sum, right? And apply twice this guy. 2 steps. First one is we take fk, which is pretty much what you want, right? So which is the sigma algebra generated by the first k variables. A nice filtration. And then we take mk. So I'm going to take out the first. Yes.
Can I ask you to make sure I understand this inequality? So if you have a martingale with bounded increments, then there's a concentration inequality that you bound very sharply the martingale.
Yes.
So here your increments are not bounded, and you want to kind of slightly relax
Yes.
it. So it's like an LP
Yes.
martingale concentration.
Yes. And again, the fact that you really need the square here, right? The proof of that, I don't remember every step. It's not super hard, but there is a clearly orthogonality arguments in all of this, but you have to write very, very carefully. This is relatively obvious, right? If I take p equal 2, as usual for this sort of things, right? So it's going to be over p, that is a bit of a pain in the neck.
Okay, and what's funny is that if you have bounded increments, you could get Gaussian control, but here you're going to
have exponential.
You take this to recover the p equals infinity case, you get exponential numbers.
Yes, you're losing something, which makes sense.
Yes.
Because your increments could be bad and then start correlating to some degree between each other.
So it's the usual loss of Gaussian exponential.
Yes.
When you try to use
Yes.
concentration.
Where was I? Yeah. So the first, I'm going to take sum over I. You're going to apply this once, and you'll get rid of one sum. And then what you'll have now are sums like this. And now you'll define another filtration. And now k is fixed, so you'll define the filtration from x1 bar till xi bar, and then you add xk, right? Or I strictly less than k. We'll have mik, that is each term in this sum, right? At each step, you're really using this, right? Those two. And that's what's going to give you the martingale property. And now I'm not going to show you the calculation. It's very straightforward. You apply it twice, right? You're losing a square root of p every time because you see that there's a square here, right? So twice, square root, you're losing a p, and then everything is nice. That's a super simple proof of this large deviation inequality. But of course, provided you knew that there was this, I should say L infinity here is not optimal. You can actually allow a little bit less. So you still need a phi to be in the correct exponential space. And if you want to make that gain, which we won't need here, but if you want to make that gain, then I don't know how to do this simply like that. And I only know how to do by the stupid combinatorics argument. But anyway, so we are happy we have the right theorem. Let's calculate the time derivative of the. I'm going to assume that we have a basic Hamiltonian interaction here. You can replace that by a divergence of k bounded, and that doesn't make any big difference. You just have more terms that I don't want to carry over. You cannot do this argument if you don't have the right bound on divergence of k. So in particular, this is pretty much useless if you're going to have gradient flow type of. We have a relatively simple equation on Fn because we have a system of coupled SDE. If I pretend that everything is okay and I just use Ito formula, I get the equation for below. Linear PDE derivative diffusion as you would expect. If the divergence of k is bounded, right? The time derivative of Fn log Fn has a very simple expression. This gives no contribution whatsoever. So you only have the diffusion, which is the usual Fisher information. Now, when I'm going to calculate d over dt of Fn log Fn divided by f bar n, right? I will try to mimic the structure with f bar n through this equation, and then I will get something that will look like the relative entropy between two heat equations, the solution to two heat equation, which is very well known, plus remainder. Now, to make my life a little bit easier, I'm going to assume that sigma n is constant. Otherwise, I would have terms in sigma minus sigma n, but I don't want to handle. I'm going to write an equation on f bar tensorized n times. And I'm going to write the same equation as on Fn plus extra terms. Extra terms, I'm going to put everything in something I'm going to call Rn times f bar tensorized n times, right? And Rn, as you imagine, is the difference between the discrete force field and the force field that you get by convolution from the limit, right? And because this has a very simple structure, I can express it in the following manner. And now I'm going to calculate d over dt, right, which is a bit of a mess, and I'm going to skip 5 minutes by assuming that we know how those terms play with each other, which again is just the standard calculation of the relative entropy for the heat equation. So we know there's a dissipation there. The heat equation is contractive for the entropy. I'm not going to look at the dissipation term, which is obviously a mistake. And you have recent papers who do look at it, and then they get better propagation of chaos. Thanks for it. But me, I'm just going to throw that out. And now I'm going to say that d over dt of Hn is less or equal than 1 over n, the interval of Rn Fn. That's it. Where again, Rn is this, right? So Rn is the reminder without f bar tensorized n times, right? And that's because I get it, of course, by taking not the equation on f bar tensorized n times, but the equation on log of f bar tensorized n times, right? So I lose this. It's a very straightforward calculation, so just trust me that this is the answer if you don't remember or if you don't know the calculation for the heat equation. And now here, I am ready to conclude. I'm going to end up using my large deviation estimate, but I just need one more step before this, right? Rn, the expectation of Rn against below Fn is not good, because I don't know anything about below Fn, and I cannot take advantage of the constellations over there, right? And on itself, Rn is a bad term because Rn is of order n, if I just bound it naively, right? Because I have a double sum and I only divide by n. So yes, I have another extra 1 over n, but then that would just give me something of order 1, which is not good. So the first thing I'm going to do is I'm going to change the Fn here into Fn into f bar n. And this is a very well-known inequality that is again just due to the convexity of x log x. And if I want to be a tiny bit careful, I can pair with a constant here and there. And then I can put divided by c here, which I will need to apply my here. As exactly the right form. See what's going on? Here I already have a difference between the convolution of k against the empirical measure minus f bar. And because of the Hamiltonian structure, because divergence of k is 0, I can get another cancellation. Actually, something that I can write in the following manner. Provided that k is in L infinity, and provided that log of f bar is smooth, then I can use my theorem. And what I get is this is less than c hn t over n if k is in L infinity and log of f bar smooth. And that gives me a very straightforward theorem. And this is another variant of propagation of chaos. And you see it's very, very different because it absolutely doesn't look at the same object. It has the same predicted value of the fluctuation in 1 over square root of n. And that's because the relative entropy is a quadratic object, right? That's because a log a over b is like plus b minus a is like a minus b squared when a and b are closed, right? So that's why you get 1 over n instead of 1 over square root of n. And as a matter of fact, if you apply a Xisar Kullback inequality on the marginals, right? So in finite dimension, then you can control the L1 norm out of this. And that tells you that the L1 norm between a marginal and f bar k times, right, is something with a constant depending on k and then 1 over square root of n. So far we are fairly consistent in terms of the scaling and the rate of convergence that we get.
Is that k c times k or c sub k?
It's c sub k.
K is like,
I think it's like k squared, if I remember correctly. It's definitely not uniform in k. So that would go up, right? Which is, again, the logic of what I was saying, the L1 norm is bad at the level of Fn.
If you don't ignore diffusion?
If you don't ignore diffusion, you can try to do something better by, instead of having exponential growth here, saying that the diffusion can control the extra entropy term that I have, right? So now it becomes a little bit harder because what you need to do is you need to do a log sub F inequality in dimension n. But if things work, and so in particular, if k is small, right? So that the constant c here is small, I could get that I have less or equal than c over n, right? And then I could get uniform in time propagation of chaos. This requires more work, so I'm not going to do it, but you know, and other people did it. There's a recent paper by Guillain, I think. It's doing exactly that. Here, that I don't need any derivatives on k, right? But I do need L infinity because that is not going to work well in any respect if you try to push phi away from L infinity by any significant amount, right? Again, I can play a little bit, I can replace by exponential. So some Maulic space would still be working, but if you try to go to phi equal in LP, this is going to break down in a very straightforward manner. What's interesting here is that you can actually push this result a little bit further relatively easily. So if sigma n, right, does not degenerate, then you can gain one derivative. So k could be in w minus 1 infinity. And that's by using the diffusion. And for first order model, right, if k is anti-symmetric, well, I can symmetrize things here by exchanging x and y. And if I symmetrize, I'll get the difference between gradient of log f bar of x and gradient of log f bar of y. And if log of f bar is smooth, that gives me an extra x minus y. And I can use that to compensate 1 over x singularity in K. But, and this is what I was saying yesterday, and this is the first example, that's not going to be working for second order, because now instead of xv, instead of x, I would have xv. So here I would have xv minus the same thing at yw, and then I would get an x minus y plus a v minus w. And K only has a singularity in 1 over x minus y. And so the v minus w times K doesn't help. So that is not working for second order. This is essentially an empty statement as well for second order, because for second order, it doesn't make sense to have diffusion in both position and velocity. You should only put diffusion in velocity. So technically speaking, it's not true that I have a non-degenerate diffusion. It is degenerate in one direction. So it doesn't apply either. So this sort of tricks, right, really lets you very easily gain one order of singularity for first order system. And it completely fails for second order. There's a last thing that I want to do today before we go tomorrow. As a preparatory statement, this tells me, gives me a bound on the fluctuation at the trajectorial level. This is something that I want to write down because it's very obvious once you have the theorem, but it's still worth noticing. So if you're in that case, what happens in the calculation that I just erased is you don't throw out the term coming from diffusion, the dissipation coming from diffusion, you keep it. And in Rn, you can integrate by part once. So if K has a derivative, you can integrate that by part and put it on Fn. And you can put the corresponding term, you can absorb it under the diffusion term, and that lets you actually gain one derivative on K.
I think it's just a misunderstanding here. Well, I think what you mean is then you can under K such that this.
Yes. All right. Thank you.
Yeah.
Thanks. So one last estimate, right, for today. Let me define now eta n, which is the difference between mu n, right, my empirical measure, scale by the right quantity. Notice that I have two competing definitions for mu n, right, which is the one when I'm using the solution to the stochastic system. And then when I'm looking at mu n with Fn, right, I replace the capital Xi by the small xi. I think that's probably obvious enough that I don't need to call them by two different names. This gives me bound on that. Test function, take a small phi, now infinity, and now calculate the expectation of the integral of phi of x, mu n dx, and let's put a square, right? This is n time the expectation of the integral of phi tensorized twice mu n minus f bar tensorized twice. And this is the expectation with respect to Fn. I'm going to play the same trick to replace the expectation from Fn by the expectation from f bar n by paying with an entropy term. This is the expectation f bar n, the right form. So provided I prepared well, right, so that initially the original entropy is of order 1 over n, then it remains of order 1 over n for all time. So this is order 1. And this is something that I'm going to use my large deviation inequality to control again. And so this is of order 1. That implies Eta n is bounded in some negative sub-LF space. So now you can play a little bit, but just take a Fourier series or a Fourier transform, right? Then each Fourier coefficient is bounded because of this, right? Because it's just the integral against phi. Phi is exponential I kx, right? So now you just need to put enough negative derivatives so that if the Fourier coefficients are bounded, then it's summable, right? Which is standard scaling of the white noise, for example. And you have a bound on the fluctuations, on the rescaled fluctuations in their corresponding sublist. And I'm going to use that tomorrow to derive an equation on eta n and to derive a limiting equation on eta n. And that is going to be extremely easy in the deterministic case, because that will give me all the bounds I want. Stop here. Yep.
Questions, comments?
Well, or the second one was a little bit harder than the first, but there's really nothing much super complicated in all of this once you have the right tools. So even if I didn't give all the calculations, I mean, trust me, the gaps here is something you can give to a good undergrad students and they can do it. So all the difficult stuff was there, right?
Is that assumption that the gradient of log of f bar is smooth?
So the problem is the log.
Yes.
Right, which sort of limits you to if you do it like that, sort of limits you to bounded domains, which would in particular be a problem for second order models where I need the velocities to be unbounded. But this is something I can improve a tiny bit if I use a better version of that. Then I don't need that the gradient of a log is Lipschitz. I only need is bounded. I only need that the gradient of a log is in some exponential space, weighted by the solution f bar itself. And this is actually compatible with Gaussian decay in unbounded space. So if you work a bit, now you need to work more because this is really painful if you want to get out of that. But once you've done the better version of this and you track down the assumptions very, very precisely, then it's not so bad there. But it's really bad here because I'm playing with another derivative of log of f bar. And that other derivative, there is no hope that now I can control it if I have Gaussian decay. So that really kills this case if you're in unbounded domain.
Moving forward that discussion, if we introduce.
Oh, just a second, just a second.
I didn't talk about anything sensible. I just following
Good.
the discussion that if you introduce a drift,
Yes.
wouldn't that bring it into the compact case?
So if you introduce a drift, right, a fixed drift,
Yeah.
so like an external field, for example, on the
For the
particles,
Laplace.
right? It's completely transparent for that. Meaning if the drift is divergence free, it doesn't create any extra term in this calculation.
Right.
Right. The issue, of course, if the drift is singular, is can you still get smooth solutions at the limit? Right. So this pushes the question actually down where I haven't discussed it. Which is I'm just assuming that I have an f bar such that log of f bar is smooth. And now if you add a bad external field, there is no particular reason why that should be possible anymore.
I'm hoping that allow you to bring the f bar above 0.
With a drift, no particular reason if it's divergence free. If it's not divergence free, then you still have to control it very, very well. So, thank you.
Thank you.